Everybody die. All right. So last time we were talking about speed conversion stuff because we're kind of on we were talking about memory, right? We're trying to wrap our minds around this idea of like the various sizes of things inside of our computer systems, and then how that ultimately is going to peel back to us in with computer programming when we talk about primitive types and things like that.
Yeah, using bits and bytes.
Yep. So all these things are very important, and we're starting to understand that the big B's and little B's are important, but then we're talking about how consumers try to get they try to take advantage of consumers and stuff, and a lot of the ads because if they can claim a bigger number, most consumers will fall for that, right? Okay, then we talked about, even though nobody in here had ever seen a movie or anything that referenced the T1 connection.
No.
Have you ever seen the movie Hackers? It's a little bit older movie, but it's kind of a fit. You've never heard of? I think it was like Angelina Jolie's first movie. It's like required reading for computer science majors. You got to watch Hackers. It's a thing. But they reference it in there. Okay, so let's kind of move past the conversion stuff for at least a few minutes. I might come back to some new stuff as we bump into it. We were talking about Java virtual machine stuff. Let's see. So we talked about the evolution of Java. We have not gotten to C# yet, right? Okay. So JVM, this is Java virtual machine. So this is a computer built in software that knows how to execute a low-level language known as Java bytecode. Okay? That's what the Java virtual machine ultimately does. It executes that. And what I mean by execute, it converts one low-level language into another low-level language. That is Java bytecode into native assembly for that operating system / architecture. So Windows / Intel assembly language, or what the example we looked at was a Linux hello world, right? So if we were running the Java virtual machine on Linux and we wrote hello world, it would convert our Java bytecode, that low-level language, into the equivalent low-level language for the Intel architecture, which is likely the processor you're running Linux on, and then specifically the Linux operating system, because it's got to use those system calls that we had talked about, right? So the virtual machine does that stuff. Now, when you think about that, what might be your concern with this Java virtual machine? I mean, I think we did. Did we referenced that Java was... Here, let's just do this. Yeah. So let's do pros and cons of Java. So here we'll have a pros category, we'll have a cons category, and certainly cons might be you're saying let's put relatively slow. Okay, it's relatively slow because it has to go through that extra step of being interpreted right there at runtime. We talked about the kind of two kinds of programming languages: compiled versus interpreted. We have that slide, right? I'm teaching a grad class that is a MSIT, so it's not computer science, that covers some of the same material, so I get a little overlapped on what I've said in one class versus the other. So we've said compiled languages are relatively fast because we convert from the high-level language to the low-level language prior to ever running it. Whereas interpreted languages are relatively slow because we do that conversion in real time while the thing's running. All right? So Java is kind of both. We compile ahead of time, but what we're doing is we're taking the high-level Java source code and converting it into low-level Java bytecode, which isn't quite ready to run directly on the CPU. Does that make sense? Needs a little bit more cooking. And that has to go through that Java virtual machine, which we could say is an interpreted step. Or the reality is today, and we'll talk about that in a few minutes when we talk about C#, is a mostly interpreted step. Now, again, we're working with this word relatively. When we say something's relatively slow on a computer, most of the time, I'm just picking a number out of the sky, let's say 99% of the time, a human being will not notice. Okay? We're not going to notice a speed slowdown in Microsoft Word if it's going through the Java virtual machine versus being natively run on the processor, because it's a business application that none of you, well, I say none of you, some of you look maybe a little bit left of center to me, but generally speaking, we're not looking at frames per second of Microsoft Word, right? It's like, yeah, I just got this new $2,000 graphics card. I'm getting 730 frames a second on Word. That's not something you say. Although I would encourage some of you to post that on Reddit and just see what kind of happens. Well, people do for games. Yeah, I mean, frames per second matter in video games, but we don't care about frames per second in word processors, right? It's not a thing. Although, like I said, post it to Reddit and share it with me on Slack so I can find out if other people think it's a thing. Because you're the one with the good graphics card here, right? We had the competition, I think, yeah. So it would be interesting to see your frames per second on Word. It's probably like 700 or something like that. Might even be higher, actually. So we say it's relatively slow, but most of the time, most of the applications we're using, that doesn't mean anything to us, right? Our computers are fast. When you go and buy a new computer today, so this is kind of back to that consumer thing, where do you spend your money? A normal human, a non-technical person might say, well, you start with the processor. 2.7 gigahertz is better than 2.3 gigahertz, and the engine's where it really makes a difference, right? But we don't necessarily fall for that in vehicles, do we? When you're buying a car, I mean, some of us might be car aficionados. I think that's the word, whatever. And you might want the muscle car, and you get the 12-cylinder V, it was the V12 with 500 horsepower. I don't know, whatever the Corvettes have or something. You get what I'm saying. The crazy powerful engine that goes 0 to 60 in 2.5 seconds or something. You don't need that, right? Most of us are driving to work or driving to, and especially when you look at a student population, many of us are not buying new cars, right? You're going out and saying, okay, what's the least amount of money I can spend on a car that will not break? Right? I mean, that's right. That's a true statement. Okay, so you don't even, as long as it has an engine. I don't care what the engine is, as long as it has one. I'm good with that.
What about tires?
It's got to have tires too. Yeah, we got those main requirements, but hey, we'll even deal with the balding tires if you can get the car cheap enough. Just when it starts raining, go slow, right? that kind of thing. But the punchline is we don't fall for it necessarily on things that we know a lot more about. But when you come down to computers, well, 2.7 gigahertz must be way faster than 2.3, and that's going to be so meaningful to my life in the computing world, right? When most of what I'm doing is checking email and doing word processing, all right, for most people. Now, the place you spend your money first on your computer, anybody know? If you're buying a computer, you're on a budget, where do you spend the money first? Not the graphics card. Well, you do need a graphics card. So this comes back down to like tires, right? Okay. You need something that will output something to a screen. Yes, that's true. But you don't spend real dollars on a graphics card. There's probably two reasonable answers to that question. One could be RAM. Probably should be RAM. You want to have enough system RAM to do what you want to do. That doesn't mean max your memory. But, if you're a relative power user, maybe 16 gigs. If you're, just a entry-level computer, get 8 gigabytes of RAM. That's going to hold you for a while. You don't have to look at performance RAM or anything like that. Just get enough memory. That's important. But the thing you probably feel the most on your computer in terms of performance, anybody know? Huh? CPU. I already said CPU stupid. That's that. You just fell into the trap after I said it. Not the CPU. Again, you need to make sure you have a CPU.
You already said memory.
Yeah, memory is important, but in terms of from a consumer's perspective, what they will actually feel when you think your computer is going slow versus, oh, my computer is really snappy, it's fast.
Hard drive.
Hard drive.
Solid state drive.
Hard drive. Big time. So if you want to see the extremes of it, go with like a budget pleaser mechanical laptop hard drive running at 4,200 RPMs or something like that, versus one of the latest, greatest solid state drives that are super, 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 super fast. It'll be night and day. If you put those two hard drives in the exact same computer, all other things are the same. It'll be night and day, the speed difference. Because everything you're doing on your computer is accessing the hard drive. Make sense? So hard drives where you want to spend your money. And some of you, from, again, the consumer awareness thing, sometimes you'll be speccing out a computer and you'll see a machine comes with and you don't maybe see this as often now because we've transitioned into the solid state drives, but a couple years ago you'd have seen this pretty often where a laptop came with let's say a 1 terabyte hard drive. And you could upgrade for $250, let's say, to a 500 gigabyte hard drive, half the size. We learned about that a couple classes ago, right? So you could pay $250 more for half the capacity. And most consumers are going to look at that and say, that's got to be a typo, right? Why would I want half as much for twice the price or something like that? It doesn't make sense. It came down to the RPMs of the hard drive. A lot of times that 1 terabyte hard drive was 4,200 RPM or 5,400 RPM. That's how fast it's spinning, right? Compared to the 500 gigabyte might have been 7,200 RPM. Spinning faster means reads and writes happen faster. So we're going to feel that. Capacity is not how we measure our hard drives in terms of performance. Capacity is how we measure our hard drives in terms of the amount of crap we can hold. Okay, so a lot of people who get who build a performance computer, what they'll do is they'll spend their money on like a 120 gigabyte or a 256 gigabyte solid state drive that's high performance. That's where they put their operating system and applications they maybe launch very often. And then they go out and buy the budget pleaser, 3 terabytes, slowest whatever. I want capacity. Okay, I don't care how slow it is. I want capacity, and whether it's an external USB one or an internal IDE hard drive if you're building a desktop, that's their secondary drive. They're not going to feel that in terms of performance. That's where they store their images, their songs, and things like that. Because when you go and play your playlist on iTunes or whatever you're using, you're not going to feel that extra little fraction of a second load time it's going to take to load your song, right? In that one moment. But if you're having everything happening on the computer, reading and writing off that slower disk, you're going to feel that. That all adds up to real time. So that's what the performance machine people do today. They get really, really, really fast, smaller capacity drives. They don't get smaller capacity out of choice. They get smaller capacity out of budget, right? It's like, okay, well, I can get a really fast 120 gigabyte drive for the amount of money I can afford. Or I can get a really, really fast 1 terabyte solid state drive today, or I can get a car, that type of thing. So the size, I would say, need is out the window when it comes to capacity of solid state drives today. I would say you always should get the higher performance, lower capacity, because realistically speaking, we could all fit the stuff that we use very, very, very often on a 120 gigabyte solid state drive. You could fit your operating system on there, because loading your video games on there actually doesn't necessarily help you that much, except for just the initial load time of that game. Now, realistically speaking, if you're playing one game all the time, because there's likely read and writes back to the hard drive during the game, it would probably benefit you. But 120 gigabytes is enough to work with for most people. You can get by. Okay, so pros and cons of Java. We said it's relatively slow, but again, that's a very relative statement. All right, so For most types of applications, we're not going to feel that, but every now and then we will. So probably what this ultimately means is not for games. Or maybe we say not for, for the gamers in here, not for real games. You could probably pull off Angry Birds and stuff like that with Java, and that's a real game by some standards. But I'm talking about things like Battlefield and Call of Duty, things that are very, very performance intensive. Okay. Now, what's good about Java? So what's the flip side? I mean, Java's still around today. It's still really popular. It must be good for something. Go ahead.
Easier for us to manipulate and understand.
Easier for you to manipulate and understand compared to what? Okay. So you're saying Java code is easier to write.
Yeah.
Okay. I mean, I can't say that's completely wrong because certainly it's easier to write than some older languages, but Java and C#, same language. They're identical languages. Good.
Strongly typed?
Strongly typed is a good thing. Well, so are a lot of languages. Now, it's fair to maybe put that under pros from the perspective of because it's strongly typed, at least it has some decisions that lead it towards performance, towards being faster, which maybe helps this be less of a problem for many things. I think that's fair. Okay, but maybe not the main one that we're going to end up putting here. Go ahead.
Runs on virtually any kind of architecture.
Yeah, so this comes back to this virtual machine thing. All right, so Java's big claim to fame is that it's platform independent. It will run on any platform. Ooh. Runs on any platform that supports the JVM. Okay, so as long as we have the Java virtual machine on that platform, which means originally the makers of Java were Sun Microsystems. Now Oracle bought that company, so Java's from Oracle now, but it was Sun Microsystems originally. So the people at Sun Microsystems, what they did is they wrote this computer program called the Java Virtual Machine multiple times. They wrote it once for Windows. They wrote it once for the Mac, for Linux, for Unix. So they wrote that one program multiple times. They ported that one program multiple times so that Java programmers, us consumers of the programming language, not typical consumers, wouldn't have to write our software for all the different platforms. We can write our software once because we're targeting one machine. The machine we're targeting is the Java virtual machine. And that Java virtual machine just happens to live on Windows, as well as the Mac, as well as Linux, as well as Unix, as well as cell phones. Okay, so, the idea is that Java's claim to fame was its platform independence. Write once, run anywhere was the thing. And back then, maybe the driving force for this was video games, because you had two groups of people. You had the Windows gamers, and they were the chosen one, right? So if you were a Windows gamer, every new game that came out for Windows. Okay, but if you were the Mac gamer, you felt like you were deprived. It's like, well, I have to wait a year or two before the game comes out for Mac, if it ever comes out for Mac. So they're over there screaming, saying that, why aren't we treated equally, blah, blah, blah. And what's funny is this was kind of a perceived problem. But if you're a video game maker, and especially back then, because our world of software development has changed quite a bit. I think I talked about that first or second day of class, where we have some students in the department now writing software and making a lot of money selling software on the app stores and things like that, where that didn't exist before. If you wanted to sell software 20 years ago, you had to write your software. You had to find a publisher who was going to invest in your software. Then they were going to work with like Best Buy to get it on the shelves there. There was a lot of hoops to go through. Where now you don't even have to put pants on, right? You write your software, you upload it to the App Store, and you wait to make money. And you're in competition with a bunch of other software, but you were at Best Buy as well. So it's a lot easier to get into the business now. I mean, it's trivial. As long as for Apple, as long as you have $100 a year, you can put stuff on the Apple Store, as many apps as you want. And for Android, it's I think 30 or $35 a year to put as many apps up there as you want.
How much do you pay for each app?
It depends how much you charge for the app. I mean, both of them take 30% off the top for charging credit cards and stuff like that. So if I sell one app on Apple's App Store for $1, I get 70 cents. That's my cut.
And how many people get it, right?
Yeah, then it all depends on how many people buy it. A current trend is what? Apps are free and then have in-app purchases. So they get you to try to click on crap. Advertisements is another thing. So whenever, the more impressions, the more ads that show up in your app, the more money you make. So you make passive income from that. So many different ways of getting income from apps today, because obviously more people are going to download a free app if that looks intriguing than download a paid app, right? I mean, it makes sense. So it's a lot easier to get into the business today. Well, back then, so let's just say 20 years ago. When was 20 years ago? So it was like late 90s. Yeah, that's good enough. So let's say, yeah. So let's say 20 years ago, we're dealing with you're going out and you're writing software. So you're a video game writer. Okay, so you write software, and that the software, when you're writing software, you're trying to make money, right? Now there might be some altruistic tendencies behind the scenes there, where you're like, oh, I really want to help people, or I think my software really makes things more convenient for people. So I'm not saying that all software developers are just mean, but at the end of the day, you're spending your time and you're trying to make a living, right? So you'd like to make money. So you have two groups of people you can target. Okay, you have the 98% of the people running Windows. Okay, or you have the 2% of the people running Mac. Which group do you target?
Go for Windows.
Go for Windows. Now, that discussion I just had was the same discussion that you've heard people say that Macs don't have viruses, right? It's the same discussion. Okay. If you're one of the jerks who write viruses, who do you target?
Target the majority.
98%. Although, let's be honest, Microsoft has drastically lost some of their percent there. I think they're down to like 94 now or something.
That's it?
Yeah, they've really slid. I mean, Apple's become very, very popular. They're up to like 5 or 6%.
Yeah, but they're still going to target the higher number.
Well, yeah. I mean, so I'm being facetious. But Apple competes significantly better in the mobile market, right? And actually, when you look at specifically laptops, Apple competes substantially better in laptops as well. Windows laptops still have the majority, but it's less embarrassing. It's a better competition in laptops.
Where did you get the idea that Macs don't get viruses from?
Well, because typically if you run a Mac, you don't get viruses because the virus people don't think you're too small of a population for them to care about. Now, I could probably, if we got down to the details of it, I could probably make an argument that the Mac OS is maybe a little bit more secure than Windows, but it has nothing to do with Apple. I mean, the Mac OS today is based on OS X. Or I'm sorry, the Mac OS is based on Unix. OS X is based on Unix, which is an operating system that's been out for, 50 years. So I mean that operating system's been through its paces, is what I'm saying. Had lots of bug fixes and things made. So because it's pretty much most of the vulnerabilities that are in the Mac today, Apple put there, by trying to manipulate it into being something that's more user friendly or whatever. So when somebody says Macs don't get viruses, there is truth behind it, but it's not because they're not vulnerable to viruses. It's because they're not popular enough to get viruses. It's the reality of it. So there was a perception problem back then for the Java proponents that you had these two populations of, let's just say, gamers, but it wasn't just gamers. It was also normal software, spreadsheets and things like that, more business application type things. But still, you had that giant population difference. The Mac people viewed it as being an even playing field, right? We like, hey, we're just as important as the Windows people, but the numbers, it wasn't even close. I mean, really, statistically, the Macintosh people didn't exist by the numbers, right? But Java attempted to solve this problem, and that's a good thing. And it worked out for business type applications, especially for applications that launch out of like web pages and things like that, which we don't see that often maybe in our world. But there's actually one industry, probably maybe even the main reason, well, I'm going to say one of the main reasons, certainly the main reason prior to kind of the mobile phenomenon, everything going on to smartphones, that made Java really irreplaceable. And that's in, how many of you do any like stock investing or anything like that? I mean, it does happen younger now, so we do have a couple of people who do it. So if you go to like E-Trade or Scottrade or any of these websites, you see the thing on there where you can spend so much per month for their pro platform, or if you have enough money with them, they give you the pro platform for free. Well, that pro platform is giving you an application for like real-time stock trading type stuff. They give you a lot of tools for looking at trends and charts and all sorts of stuff. Things that most of us aren't really going to understand, but we recognize that there's people in this world that do that, and those are important things to them, right? Well, all of those pro applications are delivered through what's called a Java applet, which is basically a full Java application that launches out of a web page. So your whole trading application, that's this real-time thing you're paying $100 a month for, is a Java program. And the reason they do that is so that they can have one code base to make sure this thing performs well, all the bugs are out, blah, blah, blah. And it targets Mac, Unix, anybody who has the Java virtual machine. Makes some sense? So that's one of the reasons why Java stayed relevant. Another reason that Java stayed relevant was Google. We're about to segue into C# here in a second, but Google, they were a Java shop. Google primarily used two languages internally, Java and Python. Okay, we're going to be using Python in here, but those were Java's kind of adopted languages. Now, why do you think Google used Java as opposed to a language like C#? I mean, we haven't quite gotten to C# yet, but I'll give you a hint. C# is made by Microsoft.
Microsoft more prone to viruses.
You think Google and Microsoft are huge friends?
I don't know.
Yeah, they're not really buddies. Yeah. So Google doesn't want to be reliant on their competition for their development. That makes sense, right? So they chose Java as their internal language, and that's all fine and good. So that's another reason why Java kind of stayed relevant. They were propped up by a big company. All right, so let's take this slide, evolution of Java. Kept variables, kept arrays, kept classes. They got rid of structs, just as a reminder. So they got rid of structs here. And they also did something. They removed the specific syntax for pointers. And we talked about that, but let's just add it to the list here. Here's that special syntax we were talking about. They removed that guy for dealing with pointers. All right, remember pointers are memory address stuff, right? So Java took away our control over memory addresses because it was fixing the problem from C++ of allowing us to make poor decisions, handing somebody the house instead of the address to the house. Okay, so Java did all this stuff. Now the big problem here, though, is they got rid of structs. Well, one of the big problems, they got rid of structs because they said that a class that is a class that you choose not to put procedures into or methods into is the same thing as a struct. And in many, 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 many ways, it acts the same as a struct. But we did talk about pass by value and pass by address, I think. Isn't that in here somewhere? Yeah, variable passing. All right, so pass by value, when we hand somebody the house, okay, this is a copy of the thing. So if I hand you a copy of my house and you paint the garage, my garage back home is not affected. Okay, if I give you the address to my house and you run to my house and paint my garage, I'm going to find out about it when I get home, right? Well, the problem here is that by default, Okay, if the programmer doesn't deviate from the plan, when you pass an object, when you pass a class, it's passed by address. Structs are passed by value. So the default way that these two different things are passed to procedures is not identical. So to say that a class that does not have methods is the same thing as a struct, which a struct is just a collection of variables. So if you have a class that you chose to be just a collection of variables versus a struct that is by default a collection of variables, when you pass those two guys without doing anything special, they are actually passed differently. Okay? Now, this only will impact you sometimes when you go and actually try to change that value internally. Now, this becomes a problem. So, for instance, if I pass you my house by address, and you go to change that by spray painting the garage door, I will recognize that side effect. The outside world, the person that passed it to you, everybody else, they're going to recognize that side effect because you were manipulating the address, the thing at the address. Where if I pass you a value, okay, so I pass you a struct, and you spray paint the struct, we're not going to notice that side effect out here. Now, that's fine if we know that's what's going on. But again, a lot of times beginning programmers, they're not necessarily aware of these little nuances, right? So you might be passing something expecting that changes in here have side effect, that they do affect things out here, or you might be passing something expecting that changes that happen in there don't affect this world out here, and you might be surprised by your result because you didn't understand the nature of that pass. Does that make sense? So to say that a class and a struct are identical isn't quite true. And it may not impact you most of the time, but that's just out of sheer luck. It's out of the patterns of how these things typically get used, as opposed to your real knowledge, which then makes that type of thing difficult to debug. Because you might be passing a class, maybe you were a C++ programmer, and you were used to structs not changing and classes changing when you passed them. You might not even have known why. You might just have recognized the pattern, right? It's like, well, when I pass a struct and I try to change it, nothing happens out here. When I pass a class and something changes, something happens out here. That's just the way they work. You might not necessarily know why. You might not understand the pass by address versus pass by reference or pass by value thing, but that's just how they work. It's fine. We get used to that. We get used to the patterns, and sometimes that's okay. But now you go to Java and you're expecting similar behavior. And you figure, oh, well, I can do a struct with a class, no harm, no foul. They took away structs from me, but I still have this power tool here. I can still pull it off. You pass a struct and you expect it to behave the same way as they used to behave. They don't. So now it becomes something that's difficult to find your bugs in your program because you might assume that this isn't the problem. The problem is not that I passed it wrong and it changed out here when I didn't expect it to. So you're hunting around every other place looking for the problem. You're changing stuff all over the place. Kind of like when you lose something in your house and you're sure you didn't put it in the place you actually did put it, and you check everywhere else. Finally, you find it in the place that you were sure you didn't leave it. That was the last place you checked. And that happened to me yesterday. I left my phone downstairs. We were installing a new filter in the furnace. And I didn't want to walk down the stairs, so I just assumed I had to go find it. So I just assumed I must not have left it down there. I made my wife go and get it. So my knee was hurting. So, in any case, knowledge of what's happening under the hood is very important for our debugging skill set, because that's more times than not, that's what's important. Fixing our problems, not solving them perfectly the first time around. So if I take this slide and we're going to say, how does this change when we go to the evolution of C#? And let's add C# to our picture up here if we haven't already done so. So there's Java. I'm going to throw C# kind of right over here. Notice it's soon after Java, so this is probably right around 1999, 98, 2000 range, something like that. So Microsoft, in Microsoft style, stole Java. They said, hey, we like Java. Programmers seem to like Java. Microsoft even released products based on Java. They had a language in their Visual Studio suite called J++, which was Java syntax that ran on Microsoft's platform. Then they even released an upgrade to that called J#, which was still Java syntax. Now, generally, so this is kind of the practice of not just Microsoft, but big companies, right? They steal stuff, and then they pay the court fees to make it okay. So if you're some kid who wrote some software in their underwear, and Microsoft steals steals it from you, and then you complain and say, hey, that was mine. Okay, give me my ball back. Microsoft says, there. Here's $1 million. Go away. What do most of us say? Okay, now I can afford pants. We go away. We weren't going to make $1 million off it. We probably didn't have the resources to market it to make that kind of money. We couldn't get onto the shelves at Best Buy to make that kind of money. So we made our money. That was what we were hoping would happen. Microsoft fulfilled our dreams by stealing from us. Now, the problem here is Microsoft stole from the wrong person. They stole from Sun Microsystems, which isn't just some kid in their underwear, right?
They have the resources.
We're a big company. So Sun Microsystems is a company in Silicon Valley. They were a big hardware maker. They made Sun Spark stations, and they had a whole arc. I mean, they were a competitor with Intel. Sun Microsystems made a processor called the Spark chip. I mean, they were a big server. They did a lot of servers. A lot of universities, a lot of enterprises ran all their web servers and stuff on Sun Spark stations. I mean, they were a major hardware manufacturer. Not the type of place you're just going to roll over and play dead against Microsoft. So they went to court. Microsoft lost, and they had to not steal Java. Okay. Well, so Microsoft said, obviously Java has a lot of stuff going for it, but as we've seen historically here, all these languages so far stem from C, right? We see that we find problems, so we upgrade. We find problems, so we upgrade. Certainly, Microsoft could say, okay, well, now we have to play nice. We can't just use Java, so we can go create our own language. But we can take what we learned from Java and maybe improve upon it. Because Java can't say that they own the if statement because they took that from C++, which took that from C, right? So a lot of the syntax are identical. If you look at a Java or a C# program today, and then you look at, let's say, the equivalent program, that solves the same problem in C++ or C, they're going to look, I'll just throw a number out there, 85% identical. Largely the exact same stuff. Just little nuances, little changes. But sometimes those changes are architecturally behind the scenes. Okay? So these languages are all C-based languages, which goes back to what I said to begin with, that all these languages are created the same. So if you understand programming as a skill set, it doesn't matter which language you're fluent in. You can pick up another language pretty quickly. All right? Now, with C#, we kept variables, we kept arrays, we kept classes. They technically sort of kind of brought structs back, but I'm not going to give them credit for it yet, so we'll just leave that off. But they brought back the specific syntax for pointers, but only within an unsafe code block. Only within an unsafe code block. So what C# did is they said, look, we realize that sometimes having the ability to manipulate memory is helpful. Java was right in their thinking that taking that syntax away protects the programmer from themselves. But they were wrong in completely taking it away, not allowing a programmer who does know what they're doing to take advantage of that tool. So C# said, look, if the programmer knows what they're doing, they'll know enough to say, look, I'm about to manipulate memory here. I'm going to wrap that inside of, you put the word unsafe, then some curly braces, and you put your unsafe crap in there, and you say, look, I'm going to manipulate memory. I know I'm doing things that are potentially destructive. Trust me, I know what I'm doing. Just like when the electrician comes to your house and starts doing stuff, right? He does the right stuff and turns power off, unlike me, where I just start sticking screwdrivers into sockets.
And you electrocute yourself?
True story. I flew across the room. My wife, I got in big trouble. I had a 4-hour timeout. It actually is. No, I completely realize that now. Yeah. I mean, I wasn't completely stupid. I was just taking the screws off this thing because I was replacing the plate. It's like, oh, well, you need to take the power off for that. But a lot of that stuff in there is metal. You know?
Conducts electricity.
Yeah. A lot. I mean, I think, oh, I'm a pretty big guy. I mean, what am I going to get a little jolt? It threw me across the room. I mean, I flew 5-6 feet.
Did you have a plastic handle on your screwdriver?
No, he just
I don't remember, but I must have been maybe touching the metal of it, like because I was like being precise. I don't remember. This happened, and now I'm not allowed to touch that stuff.
Yeah,
So.
I wouldn't allow you to touch it either.
Yeah. But it is funny that how it's almost like akin like I think husbands end up getting treated kind of like 5-year-olds. We get timeouts and we get in trouble, we get grounded. Yeah, the stuff happens. I've been married. How long? I've been married. Be 17 years in May. Yeah, so now I'm pretty well trained now. Yeah, so it's
Your house broken?
yeah, there's a lot of truth to that statement. It's unfortunate, but yeah, what are you gonna do? All right, so they brought back the specific syntax to empower the programmer who did know what they were doing to do some stuff. Okay, now let's kind of finish off today by having this Java virtual machine discussion as it relates to C#. So a computer built-in software. I'm sorry. I want to look at this execute statement. I got to spell that better, right? Execute. Yeah, whatever. So the idea, and let's actually just draw a picture of what that looks like. I think that's the better way of doing this. For Java, we take Java source. Let's kick it like this. Which then goes through a compiler, the Java compiler, which turns into Java bytecode, which then runs through the JVM, which then turns into native assembly for that platform, which then runs on the CPU. All right, so yeah, but this is a compiled step. This is an interpreted step. So this is Java. And then let me, in our last minute here, show you the C# version of this. C#. We take C# source code, goes through a compiler, turns into Missile code, Microsoft Intermediate Language, which let's just call that the same as Java bytecode. which then runs through the .NET component architecture, which turns it into a native assembly, which runs on the CPU. So at a glance, these guys look the same, right? So let me just start a slide for next time. What's the diff between C# and Java? Now, for your reading, you guys have finished chapter 1 now? Okay. Give me 1 second here. I just want to look at where chapter 2 starts you.
So we need to subscribe to the book.
Let's just limp into chapter 2. Let's look at 2.1 and 2.2 of chapter 2. Okay? Huh?
You have to subscribe to the book.
Yeah. You haven't subscribed to the book? You've had a whole chapter of reading assignments from the book that you're being graded on.
I already read all of them. Yeah, you can do the first chapter free.
Oh, you can do the chat. Well, I mean, you're getting like points if it'll help you on exams and stuff like that. If you're for partial credit, if you have proven you're keeping up with the book. Yes, you have to subscribe to the book for the course.
Oh, dang. I have it. Yeah, I've done some of it.
I've done chapter 1.